For this question, we're given the function h of x equals cosine of 3x over 2. We're restricting our interval for x from 0 to 2 pi. And we want to identify the open intervals on which the function is increasing or decreasing. Now, to do this, we need the derivative. When the derivative is positive, we know the function is increasing, and when the derivative is negative, it's decreasing. And it's going to change from increasing to decreasing when the derivative is 0. So we're going to calculate the derivative and follow a process to identify these intervals of increasing and decreasing. So to calculate the derivative, I notice that I have a function cosine of 3x over 2. This is a function where I need to use the chain rule because I have one function, 3x over 2, inside another function, cosine. So I'm going to follow the chain rule template, the chain rule derivative, where I calculate the derivative on the outside function. The derivative of cosine is negative sine. Then I'm going to leave the inside function the same, 3x over 2, and then I'm going to chain by taking the derivative of the inside function. So the derivative of 3x over 2 is 3 over 2. So that gives us a derivative of negative 3 over 2 sine of 3x over 2. So from here, what we want to do is set this derivative equal to 0 and solve. And this, when we set it equal to 0, we're finding the critical numbers. The critical numbers are going to be the place where it changes from increasing to decreasing, possibly. So to set this derivative equal to 0, we would have 0 equals negative 3 over 2 sine of 3x over 2. I can multiply both sides by the reciprocal of negative 3 over 2. So I'll multiply by negative 2/3 on both sides. So this will cancel out that negative 3 over 2 on the left, and negative 2/3 times 0 is 0. So now we want to solve the equation sine of 3x over 2. It would be helpful for us to look at the unit circle to do this, but I do want to mention here that we do have a restriction that x can be in between 0 and 2 pi. So when we look at our unit circle, we're going to have to compensate for the angle inside of sine not being just an x. So I want to take this restriction of x being in between 0 and 2 pi and figure out what our restriction is on the angle. So take that inequality, and I'm going to multiply 3 over 2 onto every part, all three parts. So 3 over 2 times 0, 3 over 2 times x, and 3 over 2 times 2 pi. So this gives us 0 is less than 3 over 2x is less than 3 pi. So we know that our angle that can be inside of sine can be anywhere from 0 to 3 pi. So let's take a look at our unit circle and now solve this from 0 to 3 pi. We want to know when sine of an angle is equal to 0. So sine is the y-coordinate on the unit circle. So we've got pi here. Here's another place when the y is equal to 0. That's when sine is equal to 0. And we're going to use 2 pi. We're not going to use the 0 because the 0 is not included. But since we're going from 0 to 3 pi, we've got one rotation of the circle and then a half rotation of the circle. So it does include 2 pi. So we have two places where sine is equal to 0, and that's going to be pi and 2 pi. So sine of pi is equal to 0, sine of 2 pi is equal to 0. But remember, we have this different angle here. So we need to set that angle, 3x over 2, equal to pi to figure out what x is. So we'll multiply by 2 over 3, and we get x equals 2/3 pi. 2 pi over 3, and we'll set 2 pi equal to 3x over 2, multiply by 2/3, and we get x is equal to 4 pi over 3. So these are the angles where the derivative is equal to 0, and these are the critical numbers, and this is going to help us identify those intervals of increasing and decreasing. These are going to act as the boundary points. So we're going to draw a number line, and we're going to include our restrictions from 0 to 2 pi. We're going to include our critical numbers. So we're only considering from 0 to 2 pi, and then we've got 2 pi over 3 and 4 pi over 3. So then we want to test each one of these intervals. We are going to test them into the derivative to see whether the derivative is positive or negative. If the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. So I'll use this unit circle to help me get the test points. The first interval goes from 0 to 2 pi over 3. So here's an angle of 0 and an angle of 2 pi over 3. I want to make sure that I choose a test point in that interval. So I'll choose pi over 2. Then I have the interval from 2 pi over 3 to 4 pi over 3. So I want to choose something along this section. I'll choose pi as my test point. And then from 4 pi over 3 to 2 pi, I'll choose 3 pi over 2. So we're going to test these in the derivative. So I've got my test points of pi over 2, pi, and 3 pi over 2. And we're testing those into h prime of x, which remember is negative 3 over 2 sine of 3x over 2. So we've got negative 3 over 2 sine of 3 times pi over 2 over 2. And that's negative 3 over 2 sine of 3 pi over 4. So 3 pi over 4, let me highlight that on the unit circle. 3 pi over 4 is right here. Sine is the y-coordinate, square root of 2 over 2. So we've got a negative 3 over 2 times a positive square root of 2 over 2. This works out to be a negative number. So I know that on this interval from 0 to 2 pi over 3, the derivative is negative, which tells me the function is decreasing on that interval. For the next point, I'll substitute pi in, negative 3 over 2 sine of 3 times pi over 2. So 3 pi over 2 is right here. Maybe I should highlight it like I did last time. And the y-coordinate is -1. We've got -3 over 2 times -1, and negative times a negative is a positive. So we get on that interval from 2 pi over 3 to 4 pi over 3, the derivative is positive and the function is increasing over that interval. And then finally we have the test point of 3 pi over 2, and -3 over 2 sine 3 times 3 pi over 2 over 2. And let's see, that fraction reduces to 9 pi over 4. And 9 pi over 4 is the same thing as pi over 4 when we rotate around the circle. So the y-coordinate is positive square root of 2 over 2, so we have -3 over 2 times square root of 2 over 2. That works out to be a negative. So our function is decreasing on the interval from 4 pi over 3 to 2 pi. And so now we can state our intervals of increasing and decreasing. We know that the function is increasing from 2 pi over 3 to 4 pi over 3. The function is decreasing on two intervals from 0 to 2 pi over 3, as well as 4 pi over 3 to 2 pi. For this question, we want to determine whether the mean value theorem can be applied to the function f on the closed interval from a to b. Our function f is 2 sine x on the interval from 0 to pi. So I've stated here the mean value theorem. If f is continuous on the closed interval ab and differentiable on the open interval ab, then there exists a number c in that interval AB such that the derivative at c is equal to f of b minus f of a over b minus a. So both of these represents the slope. This is the slope of the tangent line, and this is the slope using the endpoints of the interval. So in order to determine whether mean value theorem can be applied, we need these two conditions. We need the function to be continuous, and continuous specifically on that interval. Our function 2 sine x is a function that is continuous over the whole real numbers, so it's certainly continuous on the interval from 0 to pi. Then the derivative of 2 sine x would be 2 cosine x, and that derivative is defined on all real numbers, so it's also defined on this interval from a to b from 0 to pi. So the conditions of mean value theorem are met. The function is continuous and differentiable on the open interval from 0 to pi. So now that we've established that mean value theorem can be applied, we want to find all values of c in the interval from a to b, that the derivative at c is equal to f of b minus f of a over b minus a. So essentially we've got an equation to solve here. What I want to do is I want to work out the right-hand side of this, f of b minus f of a over b minus a. That's going to be f of pi minus f of 0 over pi minus 0. So f of b, f of pi, that's 2 sine pi minus 2 sine of 0 over pi. And sine of pi, that's the y-coordinate. So on our unit circle, the angle of pi would be here. That ordered pair is -1, 0. Sine is the y-coordinate. So we get 0. 0 minus. And sine of 0, the angle of 0 is here. This is the point 1, 0. Sine of 0 will be 0. So we get another 0. 2 times 0. So we have 0 over pi, which is 0. So now we have the right-hand side. The derivative at c is equal to 0. Now I've already calculated the derivative up here, so I can substitute that into the left-hand side. 2 cosine of c equals 0. And now I want to solve this equation to see when cosine is equal to 0. I'm going to divide by 2. And that gives me cosine at c is equal to 0. So on my unit circle, cosine is the x. So I've got here the ordered pair 0, 1. Here the ordered pair 0, -1. Both of these places have cosine equaling 0. But remember, my interval is from 0 to 2 pi, so I'm only going to consider this one right here. So this angle is pi over 2. So cosine of pi over 2 is 0, and that gives me c is pi over 2. So c lies in that interval from 0 to pi, and the derivative at pi over 2 is equal to f of pi minus f of 0 over pi minus 0. So this is saying that the slope of the tangent line at pi over 2 is the same as the slope of the secant line using 0 and pi. For this question, we want to find the critical numbers of the function g of x equals 2x squared times 8x. Now, the critical numbers of a function are going to be when the derivative is equal to 0 or the derivative is undefined. So we need to calculate the derivative. Now, the function that we have is 2x squared times 8x, 8 to the x. This contains a product, so I'm going to need to use the product rule to calculate this derivative. So calculating the derivative, I'm going to treat 2x squared as my first factor and 8 to the x as my second. I have the first factor, 2x squared, times the derivative of the second, 8 to the x. So the derivative of a to the x is a to the x times ln a. So this is going to be 8 to the x times ln of 8. That's the first factor times the derivative of the second factor, plus the second factor, 8 to the x, times the derivative of the first. So that will be 4x. Okay, so let's clean this up a little bit. We can factor out 8 to the x. We can factor out a 2. We can factor out an x. So if we factor those out, we'll get an x times ln 8 plus 2. So we have 2x times 8 to the x times x ln 8 plus 2. So the critical numbers are going to be when this derivative is equal to 0. So let's set it equal to 0. And if I set each factor equal to 0, I've got 2 to the x equals 0, 8 to the x equals 0, x ln 8 plus 2 equals 0. So 2x equals 0, I'll divide by 2 to get x equals 0. 8 to the x is always positive, so this gets no solution. And on this one, I will subtract 2 on both sides. X ln 8 equals negative 2. Divide by ln 8. And I get x equals negative 2 over ln 8. Now, this derivative is never undefined. I'm taking a look at my different variables here. I've got 2x. That's got a domain of all real numbers. All right, that's 2x. I can plug any number into that. 8 to the x, I can plug any number into that. X, I can plug any number into that. So we don't get any more critical numbers from considering when the derivative is undefined. Thank you for checking out my videos. Have a great day.